So hello everyone and welcome to the 6th FoCM online seminar. My name is Markus Bachmeier and I'll be your chair today. And today we again have two excellent speakers. First, Rebecca Willett, and about an hour later, Sebastian Reich. So before we start, let me mention that the lectures are additionally broadcast live on YouTube, and recordings will also be made available on the same YouTube channel with links to the FoCM website. And if you'd like to ask a question, you can post it in the chat, or you can also raise your hand. And if there's an urgent question, you can also post it during the talks. So we now come to the first talk by Rebecca Willett. She is professor of statistics and computer science at the University of Chicago, and her research is focused on machine learning, signal processing, and large-scale data science. Willett received the National Science Foundation's Career Award in 2007, an Air Force Office of Scientific Research Young Investigator Program Award in 2010, and was recently in 2021 also named a SciM Fellow. And today she will speak on machine learning and inverse problems, convergence and adaptation. So please, Rebecca, the floor is yours.
Thank you very much. It's a huge honor and pleasure for me to be speaking with you all today. And to tell you about some of the work that I've recently been doing with my group at the intersection of computation and mathematics and statistics in the context of trying to solve inverse problems using machine learning. So in particular, this is joint work with my former student, Davis Gilton, who's going to start a new job at Microsoft any day now, and former postdoc Greg Ongi, who's now a professor of mathematics at Marquette University. So the general class of problems that we're interested in are inverse problems in imaging. So what I mean by that is that we have an image of interest that ultimately we'd like to recover, and we're going to call that X. So it could be an image of Albert, or of a plane in a field, or a bird, or even a picture of some part of your body internally. But we don't get to observe those images directly, but rather we get to observe linear projections of them, or distorted observations. And mathematically, we can model that as we collect a vector of observations y that corresponds to the multiplication of some sensing matrix x plus, sensing matrix A times x plus some noise epsilon. So for instance, if we were interested in painting, the problem would be that we don't get to observe all of the pixels in the image, but rather there's a collection of pixels that have been blocked out, in which case this forward model, or sensing matrix A, would be a subset of the rows of an identity matrix. Or alternatively, we might observe a blurry version of the image so that A is a circulant matrix corresponding to some low-pass filter operation. We might observe a low resolution version of the image that we want to recover. Or in settings like MRI, we might even be observing the Fourier transform coefficients of the image, or even just a subset of them. So in this depiction here, the white pixels correspond to locations in Fourier space where we collect a measurement, and black pixels correspond to places where we have no data. So we've got fewer Fourier coefficients than we have pixels that we'd like to recover. So in all of these cases, the problems are generally ill-posed, and there are potentially many solutions to this set of linear equations, and we need to somehow figure out a way to recover the correct, or a good image X from these observations Y. So this is a very old problem. People have been studying it for many decades. And just to kind of highlight where some of the challenges arise, we could take the example of deblurring. So again, we imagine that our observation y is equal to ax, potentially with some noise. So in my picture here, this is an example of a times x. So it's this image of the cameraman after going through some blur operation. And in the upper left here, there's no noise whatsoever. Epsilon is 0. And so if we were to take this noise-free image and try to estimate what the original non-blurry image X was by just doing least squares, then we have a simple closed form expression that depends on our observations and our forward model A. And if we do some simple linear algebra, we see that that least square solution is the true image X that we're interested in, plus another term that depends on the noise. And if there's no noise, that term goes away and we exactly recover the original image. The challenge arises when we have, for instance, a small amount of noise. So here you can see an example where I've got a noisy and blurry image, and the noise is very small. It's imperceptible to you or me. But when we try to use something like this least square solution, things start to fall apart. And the issue is that this forward model A has some very small singular values. So that when we take A transpose A and try to invert it, then we get some large eigenvalues that, I'm sorry, some very tiny eigenvalues that have to be inverted, resulting in a matrix with some huge elements that gets multiplied by epsilon. And so in practice, what happens is that this term becomes enormous and drowns out the image X that we're trying to recover. So even with a tiny, almost imperceptible amount of noise, when we try this least square solution, we get a completely useless result. And so the general framework that people use to address this problem is that of regularization. And one of the oldest forms of regularization is Tikhonov regularization, or in statistics communities, we might refer to this as ridge regression. And the idea here is that instead of trying to find an image X, which minimizes our sum of squared residuals, we're going to seek something that's good in terms of the fit to the data, but also where none of the estimated pixel values are too big. And this is a particularly nice form of regularization because this has got a nice closed form expression. And we can see that what happens is that now the matrix that we have to invert is guaranteed never to have eigenvalues that are too tiny. And so everything's going to be relatively well behaved. And if we try this out in practice, we get a reconstruction that looks quite a bit better. It's certainly imperfect. We can see all kinds of ringing artifacts, and it's still a little bit blurry, but it's significantly better than what we could get with least squares. So in general, this notion of trying to minimize how well we fit the data, plus a term that reflects some sort of information about the image, such as, oh, none of the pixels should be too huge, is a general concept that's been explored in a lot of different ways. And the basic idea is that we try to develop geometric models of image structure that reflect some kind of prior information about the space or distribution of images that we might want to recover. So when we talk about finding a good regularization function, it's sort of like saying we want to find a negative log prior for the space of images. And over the decades, there have been many examples of such regularizers being developed, including by many of the people in the audience here today. So some classical and important examples include, for instance, total variation, where we would take an image and look at all of its first order horizontal and vertical pixel differences, and then just compute the sums of the magnitudes of those differences. Alternative regularization schemes correspond to taking, say, the wavelet transform of an image and computing the L1 norm of all of those wavelet coefficients, or even trying to exploit low-dimensional manifold structure or subspaces among small patches extracted from an image. But in all of these cases, the way we came up with these regularizers is we sat back and we said, what kind of structure do we think images should have? Should they have somehow redundant patches, or should they have smoothness with smooth boundaries? And then we tried to develop mathematical tools that reflected that general intuition. What I want to talk about today is an alternative paradigm where we're still going to focus on trying to find an image that's a good fit to the data and has a small value of some regularization function. But instead of just fixing this regularization function a priori based on some notion of smoothness or image geometry, what I'd like to do is to take a large collection of training images or example images, and from that, learn a function R that reflects that geometry of or distribution of images and use it to perform this regularization task. So the general pipeline that we're going to consider today is the following. We're going to imagine that we start off with a whole bunch of XY pairs. So we've got a whole bunch of, say, clean images, and then a whole bunch of distorted images. Let's say blurry images for the sake of argument. So all of these pairs share this general form where yi is a times xi plus some noise epsilon I. And then what we're going to do is we're going to take these pairs and try to train, say, a neural network to learn a function that I'm going to call f of theta, where what f of theta is going to do is it's going to map a distorted image y to a reconstructed image x. So we're going to look for a reconstruction network or a reconstruction function that over the set of training images that we've collected does a pretty good job of taking us from a distorted image to a clean image. And once we've selected that image, then when we get a new distorted set of measurements, then we can just plug those in and get a reconstructed image back out. So a number of people have been interested in this general task of figuring out how to choose a reconstruction network or reconstruction mapping that essentially is performing a regularization role. And what I want to do today is, instead of giving an overview of the dozens and dozens of papers in this area, is kind of focus on some of the key trade-offs and mathematical challenges that arise within this general context, and some of the approaches that we can take, and some of the ways that understanding the underlying mathematics can play a huge role in developing better approaches. So the first trade-off that we're going to explore is between generality and sample complexity. And in particular, what I mean by this is that we said that A, this matrix A, is going to reflect how our measurements are distorted relative to our original image X. And so I want to consider what happens if we use knowledge of that A during training or not. And there's a couple of ways you could imagine, thinking about this. The first and perhaps simplest is to say, what I want to do is I want to just start with a really rough reconstruction and then train, say, a neural network to correct all of the errors in my initial rough estimate. So here's an example of that idea in the context of super resolution. We start with a low resolution image, and then we map it to a higher resolution image, say using bicubic interpolation. So this is sort of like saying, I've got a very loose, rough idea of what this forward model A is, and I'm roughly going to invert it, but I'm not using precise targeted information about exactly what A is. And so when I do this bicubic interpolation, I mean, it's okay, but there's definitely a lot of blurry or blocky artifacts that result. And so then we could train, for instance, a neural network to just map these images with blurry and blocky artifacts to reconstructed images that are crisp and clean and have a lot of nice detail in them. And so for some problems, like super resolution, this can be a reasonably effective approach, but it's not that generally applicable. So in particular, when this A matrix or this projection operator is very complex. So for instance, if it reflects, say, MRI measurements or tomographic measurements, this process takes a lot of training samples, because not only do we have to learn something about the geometric structure of images, but we also have to learn something about how those images are connected to our measurements, right? If we don't use that knowledge, then we have to learn it from our training samples. And that takes, since we're having to learn a lot more about the imaging process, we require a lot more data. And so in general, this approach is only applicable to only effective in settings where this forward model A is relatively straightforward, not too far off from an identity matrix in some sense. So now let's think about methods that use this forward model A in a maybe more principled way. And the way I want to start is by talking about optimization tools that are commonly used to solve inverse problems in imaging. So I've shown this little optimization problem a couple of times now. where the idea is that if I had a good regularization function, I would choose a good image X by finding one that solves this optimization problem, the sum of squared residuals plus the regularizer. So if I knew what that regularizer is, then I could solve this optimization problem using a number of different methods. And one example that's especially popular is proximal gradient descent. And the idea here is that we start with some initial image X and some step size parameter eta. And then at each iteration, we're going to take two different steps. In the first one, we're going to take our current estimate and we're going to update it by pushing it towards a better fit to the data. So we're taking a step in the negative direction of the negative gradient of this data fit term. So we're forcing our estimate to be a little bit more consistent with the data. So we call this our data consistency step. And then once we do that, then what we want to do is we want to employ image geometry information reflected in the regularizer by applying an operator that says search among images and find something that's close to this intermediate estimate C, but also has a small value for this regularizer. And we can think about this often as a sort of denoising step. It also has a name in the optimization literature as a proximal operator. So this is just sort of a shorthand representation of that denoising step. And we can even kind of think about this in a simple block diagram if that's helpful. So I start with some initial estimate, force it to be a little bit more, have a little more data consistency, and then apply this proximal operator to get more regularization, then data consistency, then proximal operator. And we would just do this all the way to convergence. So this is what I might do if I had a regularization function R and could just run this algorithm. So one of the ways in which people might say, if I don't have a regularizer R, I just have a training data set, is they would say, well, what if I take my training data to learn this proximal operator? Or in other words, learn how to denoise noisy images. So I could take a whole bunch of training images and add noise to them, and then learn a neural network that maps noisy images to clean images. And so once I've got that denoiser trained, I can kind of plug it in to this proximal gradient method and let it rip. And this is often referred to as a plug and play approach, right? I offline learn some denoising and then I just kind of plug it into this general framework. And so our block diagram looks kind of similar. I start with an initial estimate, apply data consistency, and then instead of using a formal prox operator, I just plug that into my denoising neural network, and then data consistency, denoising neural network, and just repeat this until convergence. So this general concept has been explored in a number of different ways and from a number of different perspectives. So there's a lot of variance on what I just described here. Like I said, some people study this under the guise of plug and play methods. More recently, people have been exploring a slightly different variant that seems to be pretty effective empirically, called regularization by denoising. And there have even been some nice studies that look at the convergence properties of these methods and try to say, well, what needs to be true about this learned denoiser to ensure that these methods actually will converge to something eventually? Well, one question you might ask is, well, how much training data do I really need to make this work? And so here's an example, similar to the inpainting problem that we looked at earlier. So we've got this original image X, and then what we observe is that image with a bunch of pixels missing. And what we want to do is be able to fill in those missing pixels. So we trained a neural network using the ideas that I described with 80,000 sample images, and we get a reconstruction that looks pretty reasonable. It's certainly not perfect, but we effectively learned that we needed to fill in an eye and a nose. But if I were to take that 80,000 samples and replace it with a smaller number, say 2,000 samples, all of a sudden this completely crashes and burns. We get an estimate that is, worse than just the original observed data. And so you might ask, well, what's happening here? Why is this failing so spectacularly? And I would argue that the problem with this general approach and the reason that it requires lots of training data to be effective can be answered through the lens of thinking about probability distributions over the spaces of images. So in particular, we've got an image Y here. And the classical way of thinking about how to do reconstruction is to say, if I have a prior over the space of images, then I can combine that prior with my data likelihood to get a, say, map maximum a posteriori estimate of the image. But one of the things that you might note from this little cartoon diagram is that there's a lot of stuff going on in this image that's totally irrelevant to my in-painting task. I don't need to know anything about the background pixels in this image to realize that I need to fill in an eye and a nose here. And so if we're trying to learn this full prior probability distribution, which is akin to like learning how to denoise all the images I might ever encounter, then I'm having to learn a lot of things about the geometry of images that's irrelevant to the task of reconstruction that I have at hand. And so what I would argue is that what we really need is something slightly different, a conditional density. In the context of in-painting, what I mean here is that I want to know what's the conditional distribution of the missing pixels given the observed pixels. Or more generally, I want to know what's the conditional distribution of all the image components in the null space of this matrix A given the observations. And this is I think, helpful insight because there's been a wealth of statistical literature that has shown that estimating a conditional density can actually require far fewer samples than estimating the full density. And there's a number of reasons for this. Often conditional densities can be smoother or they can intrinsically be lower dimensional. And so even though if we had the full density, we could compute the conditional density, going directly after the conditional density can be much more efficient in terms of samples. And so what this suggests is that if we do know what A is ahead of time, if we know what inverse problem we're going to solve, then somehow we should be using it during training because we need to learn something that's somehow a function of this conditional density. You know, the same conclusion can be reached perhaps in a slightly less hand-wavy way by saying, you know, imagine that we wanted to consider all possible mappings from distorted images to clean images. And what I'm interested in is the best possible mapping or best possible reconstruction image. So I want to find the mapping F that minimizes the mean squared error, where I'm taking the expected value over all possible XY pairs. And you can actually write down what this optimal reconstruction function F star looks like. And it has two components. One is just the pseudo inverse of A applied to our data Y. And the second one contains a factor that's the expected value of sort of the null space components of the image given the observations. So we can see that the optimal thing to do with full knowledge of this distribution depends on the conditional density. And so even from this perspective, what we see is that the thing that we need to learn, the thing that we don't already know because we know A and know Y, the thing that we need to learn depends explicitly on this forward model A. And so trying to learn something more general without using that knowledge of A is likely to be suboptimal and require a lot more data. So this insight has led to a closely related but alternative framework referred to as deep unrolling. So the first top of this slide looks exactly like we were looking at a few minutes ago. Nothing's really changed much here. The key distinction is that when we look at this block diagram at the bottom, where we alternate between data consistency and a neural network, and then data consistency and a neural network, instead of running this to convergence, we're only going to allow it to run for k different blocks or k different iterations. We're going to fix that number in advance, and then we're going to train this from end to end. So before, what we were talking about is training a denoiser and then just plugging it in. And in contrast, what we're saying here is that we are going to train the denoiser in the context of this block diagram. So we're going to kind of optimize our denoiser to work well in conjunction with these data consistency steps that depend on our forward model A. So by training, and so even though the block diagram looks pretty similar, the training mechanism explicitly depends on this forward model A, which is showing up in all of these data consistency blocks. And so we're more likely to be targeting that conditional distribution that we think is so essential to being accurately reconstructing images. And this is a pretty effective approach in general. There have been a number of different papers that have looked at deep unrolling in the guise of different optimization methods or in different application contexts. And this is just a table from a recent review article kind of highlighting a bunch of the recent works in this area. Our own group has taken a slightly different approach and said, instead of starting from an optimization method such as gradient descent or proximal gradient descent, what if we were to start from a Neumann series approximation of the optimal reconstructed image or the optimal operator for reconstructing an image? And what that leads to is something that looks on the surface kind of similar to what we described before, where we start with some initial estimate and we've got some data consistency blocks and we've got a neural network that we can train. But critically, by starting from this Neumann series approximation in the development of our system, we come up with a system that has all of these sort of red, we could call them skip connections, that do not arise in other approaches and seem to have a pretty helpful empirical effect. So I want to move on to some of the other trade-offs. So I'm just going to highlight, some of these ideas in action. And in this diagram, we're considering deblurring an image. So here's the original image and here's the deblurred image. And the top two rows only are trained using 2,000 training samples, and the bottom two rows have 30,000 training samples. So we've got a small number and a large number of samples. The colored images are the reconstructions, and the grayscale images correspond to residuals. So the blacker it is, the better. And so what we're seeing here is that these Neumann network inspired approaches and unrolled optimization approaches are doing quite well compared to methods where either knowledge of the forward model A is ignored completely, or we do all of our learning ahead of time and then just plug it into some optimization approach. And this is true not just in this one little anecdote, but across the board. So we looked at a number of different optimization problems, a number of different inverse problems, a number of different training data sets, and a number of different training data set sizes. And across the board, these Neumann network-based approaches, which leverage old ideas from mathematics that have played an important role in other fields, by leveraging them in this context, we were able to get some pretty significant performance gains as measured by peak SNR relative to past approaches. I also wanted to show you the result of these kinds of ideas in the context of MRI reconstruction. So this is sort of the true image of someone's brain that we'd like to reconstruct. And just as a reminder, this image down here is showing where we have observed Fourier coefficients of the image. So we want to reconstruct the image from Fourier coefficients in the white locations. And so these next three images are showing the reconstructions that we can get from these unrolled kind of methods, and contrast that with a total variation reconstruction, which is commonly used as a baseline in clinical practice. And what we can see is that these methods that were based on learning from a training data set are getting somewhat better accuracies, higher peak SNRs than total variation, but dramatically lower computation times. So we're able to, reconstruct the image much, much more quickly than something like total variation by using these neural network-based approaches. Okay, so what we've seen so far, when we've looked at this first trade-off, is that using knowledge of A during training allows us to get much better reconstructions with many fewer training samples. The caveat here is that, of course, if we're training with a specific inverse problem in mind, then when we change the inverse problem, we have to retrain things. And that's something that I want to talk about in a little bit more detail later. But first, I want to just talk about trying to, suck the most performance that we can out of these types of approaches that we've been describing. So in particular, when we talked about these deep unrolling methods, we said the idea is that we're going to fix the number of blocks or the number of iterations, K, in advance. And in fact, when people do this, K is typically small, on the order of 5 to 10, which is why it is so fast in these MRI settings. But that has a real impact on performance, and that's something I want to explore a little bit with you. So in this plot here, what I'm showing you is what happens. Let's just focus on the orange curve for a second. I'm training a deep unrolling method where I say ahead of time, I'm only ever going to run it with 6 iterations. Full stop. I'm just never going to run it for more than 6 iterations during training. And I train the network. And then at test time, or I deploy it, and I see how well it does on some new images. And in this chart, what I'm doing is I'm saying at test time, after my network is fully trained, I'm going to see, well, what happens if I go beyond, say, 6 iterations? Now that I've learned how to regularize the image, can I just use that regularizer, but run some optimization method all the way to convergence? And the answer is no. So what we see time and time again is that if at test time we run it for just 6 iterations, then we do well. But if we try to continue to run for more iterations to improve the quality of the reconstruction, it doesn't work. We only get worse. So then you might say, oh, well, let's train it for 10. And then you do well at 10. But again, once you go beyond 10 iterations, you don't do well. So then you might say, well, let me train it for even more, say like 14. And then things degrade in a different way, because now the network that we're trying to train is so big that we start having memory issues and computational issues and stability issues. And so the performance gets lower. And so you might ask, okay, well, are the deep unrolling methods that I've shown you so far really the best we can do? Because it seems like we can't do better by learning the regularizer and then running for more iterations. And we can't do better by learning one of these deep unrolling methods for a big number of iterations. So what's left? And this is not just a, numerical sleight of hand or anything. When we actually look at images, what we see is that, if we were to train to do well in 10 iterations and then look at the reconstruction at 10 iterations, it looks good. But as we keep on, if we were to try to keep on iterating, we start getting huge artifacts and huge errors. It never really converges. So what I'm going to show you is something that is a hybrid between a couple of the things that I've already described. So we talked about plug and play approaches where we learn a regularizer and then just plug it into an optimization method and run it till convergence. And so that's nice. We don't really have to worry about, fixing the number of iterations in advance, which is always a little bit hairy. And we're going to combine that with these deep unrolling methods, which have no convergence guarantees and in fact, demonstrably do not converge in practice, but which generally have gotten state-of-the-art performance in the past. And we're going to consider an alternative that really gives us the best of both worlds here. And the way that we do that is we leverage fixed point theory. So the idea is this: what we'd like to be able to do is to run an iterative algorithm until convergence. So let's imagine that we've got some function f that describes what we're doing at each iteration. So if we're going to run our method to convergence, then ultimately what we'd find is a fixed point of that function f. So for example, we talked about proximal gradient descent earlier, where we alternate between a data consistency step and a proximal operator step. Well, that simple block diagram or simple iterative method would correspond to a function f that corresponds to this data consistency step followed by a proximal operator, and then a fixed point of that function would be our ultimate solution. And you can make exactly the same argument if you replace that proximal operator with something like a neural network. And so what we're going to do is we're going to say, instead of fixing a certain number of iterations in advance, what we'd like to be able to do is to learn a neural network that corresponds to some fixed point equation so that the resulting fixed point is going to be a good reconstruction of the image. So instead of saying, I'm only going to run this for 10 iterations and I want the output at the 10th iteration to be good, we're going to say, I am going to run this to convergence and I want the resulting output after convergence, or after effectively an infinite number of blocks, I want that to be good. But I want to do this in an implicit way without having to actually, in memory on my computer, build an infinite number of different blocks with an infinite number of neural networks. So there's been some recent work on deep equilibrium models that effectively show us how to do this optimization using tools from implicit differentiation. So I just want to kind of give you some of the highlights of some of the ideas that appear here. So remember, the idea is that we've got a function f theta of x, where what we're going to do is take an image x, push it towards being a better fit to the data, and then feeding it into a neural network with weights or parameters theta. And now what we want to do is we want to say, well, that function f theta has some fixed point x star. And what I want to do is I want to choose theta so that that fixed point x star is good. So in order to optimize those parameters theta using something like gradient descent, what I need to do is I need to compute the gradient of my loss with respect to these network weights theta. And so I can actually split this into two factors. I look at the gradient of the loss with respect to the fixed point and the gradient of the fixed point with respect to my network weights. And it's that second factor that's really the tricky one to deal with here. But we can do it using implicit differentiation. So we want the derivative of our gradient of our fixed point with respect to our parameters. And we can calculate that by using this fixed point equation. So on the left side, I've got the gradient of x star with respect to theta. And on the right side, I'm going to take the gradient of f theta of x star with respect to theta to get this expression here. And then I simply do a rearrangement of terms and some simple linear algebra. And I get a nice simple expression for the gradient of my fixed point with respect to theta, which allows me then to make updates to theta and actually learn a good theta that ensures that the fixed points, or the result of an infinite number of iterations, is actually going to have high reconstruction quality. Okay, so you might say, well, then do these iterates. If I were to learn a good theta, and then I were to iterate this equation, will it converge to a fixed point? And the answer is yes. So if this map that we learn is contractive, then we will converge to a fixed point and converge linearly. And then you might say, well, okay, that's all well and good, but can we actually ensure that this map that we've learned with a neural network is contractive? And it turns out, yes, as long as we can make sure that the neural network that we train has a bounded Lipschitz constant, then in fact, the map will be contractive. And finally, there's been some recent work on spectral normalization techniques during training that can ensure that this Lipschitz constant is bounded. So we can actually perform this training and practice in a way that ensures that we are going to be able to converge and converge to a nice fixed point. So let me show you some of these ideas in action here. So this is an MRI example. And when I talk about eightfold acceleration, this is referring to how many samples that we have available. So this is like saying if I've got an image with p pixels, then the number of Fourier coefficients that I observe is p over 8. And that would be eightfold acceleration. So this is an underdetermined system where we've got fewer equations than unknowns. So this is the ground truth image that we ultimately like to recover. And if I were to just fill in all the missing Fourier coefficients with zeros and then do the inverse Fourier transform, I get something pretty bad, which just emphasizes how little data that we have to perform reconstruction with. And then we've got the result of these deep unrolling methods where we fix the number of iterations in advance versus our approach that runs all the way to convergence. And I'm going to focus in on this little cyan block here just to give you a little bit more detail. And what we can see is that in the ground truth image, there's these sort of diagnostically relevant features that are somewhat obliterated by the deep unrolled method, but which are accurately preserved by our method, which can run for a large number of iterations all the way to convergence. In contrast to what we saw with deep unrolled methods, if we were to take this sort of learned network that we've trained and run it for a large number of iterations, we see that in practice it really is converging. It's not introducing those horrible, ugly artifacts that we saw earlier. We can also see this numerically, where we, again, do all of our training, and then at test time, we try running our model for different numbers of iterations and seeing, depending on how many iterations we run, how accurate our reconstruction is. And we've got 3 different methods that we're comparing here. So the first, in orange, is this plug and play approach, which is the first thing I described today, where I train a denoising method or train a proximal operator offline and then plug it into a optimization routine. And so what we see is that as designed, it does actually kind of converge. It doesn't start getting worse after a while, but it never really reaches very high peak SNRs or high accuracies. In blue, we've got the result of deep unrolling, where we trained it to work best for 10 iterations. And so what we can see is then at test time, if we run it for 10 iterations, it does great. But if we run for any more than that or any less than that, we get this really steep degradation in quality. So we can only, once we've trained it to work for 10 iterations, we're stuck with 10 iterations forever. And in contrast, in red, we've got our proposed deep equilibrium approach, which achieves in a small number of iterations, gets the same accuracy as these deep unrolled methods. But if we were to continue to iterate, then the accuracy continues to increase, and we not only converge, but we converge to something that's more accurate than any other method is able to achieve. So just a couple other kind of points I wanted to make. Some people have asked in the past, for instance, well, does this deep equilibrium approach require a ton of memory or a ton of parameters? Like where's the catch? So in terms of memory, we only have 1/8 the amount of memory that deep unrolling uses. So we've got some significant savings there. The number of parameters we have to learn is the same. So we haven't incurred any additional costs there. It does take about twice as long to train. But I think that's a price many people are willing to pay. And we see in a variety of applications that we again kind of get a method that converges and converges to something better than we're able to achieve with other methods. So here's another kind of comparison point where we can look for a variety of problems, deblurring, compressed sensing, and MRI, at how well these different approaches work. So with total variation, I just put that in there as a comparison point that I think many people in the audience here would be familiar with. Then in gold and red, we've got two methods where you would learn a denoiser or proximal operator offline and then plug it in to an optimization routine. And these are doing better than something like total variation across the board. Deep unrolling leads to additional gains. And this goes back to something we talked about earlier, because deep unrolling methods incorporate knowledge of the inverse problem at hand throughout the training process. And that leads to, real empirical performance improvements. And then finally, in blue, we get the deep equilibrium approach, where we've trained this to not just work for a small finite number of iterations, but designed it so that the limit point is actually high quality reconstruction. Okay, so with that, I want to return to this list of key trade-offs. So far, we've looked at the importance of incorporating a known forward model, or knowing what inverse problem you want to solve, into the whole process. We've looked at trying to make these training processes stable, even when we want to run for a large number of iterations to get more accuracy. And then finally, I want to look at what happens when we try to learn how to solve one inverse problem, and then later on, change our mind and want to solve a slightly different inverse problem. So in particular, we talked before about how if we know what inverse problem we want to solve, then we should use that information. We know that that's sort of the right thing to do from a number of different perspectives, especially when you've got limited training data. But there are many, the problem with that is that later on, if that forward model changes, then these methods can start to break down. And I think MRI is a great example of when that might happen, right? So there are lots of different buttons and knobs on an MRI scanner that can control, for instance, exactly where we collect our samples or how much undersampling we do, coil sensitivities, magnetic field inhomogeneities. Lots of things can be different from one scanner to the next, or from one hospital to the next. And so we don't want to necessarily, train a method to do really good reconstructions and have it only work on a certain scanner under certain conditions where none of the settings have ever changed. Okay, so the question is how to become robust to these shifts in the forward model. And just as a quick reminder, we again are in this setting where we've got a bunch of XY pairs that we train from. And we're going to assume all those XY pairs are coming from our initial forward model A0. But then what we want to do is at test time, use a new forward model A1. And let me just show you how problematic this change from A0 to A1 can be. So here's a ground truth MRI image of a knee. And here's the reconstruction that we can get if we both train and test for A0. So we set up our scanner, we use it to generate training data, we train for it, and then we use it and the scanner never changed. And so we get 31.7 dB PSNR. But now in contrast, imagine that we do exactly the same training, but then at test time, there's a slight difference in which Fourier coefficients we measure. Even with that very small difference, our accuracy, or PSNR, can drop by 5 dB. And you can see visually like big errors that have been introduced by this small little change in the forward model. And this is an effect that's been noted by a number of authors, maybe most notably a group at Cambridge that talked about this a couple of years ago. So I'm sure many of you are thinking to yourselves, well, I know how to solve this, right? I'm just going to, every time I tweak my MRI scanner, I'm just going to retrain. You could do that, but it's pretty computationally costly. And in settings like medical imaging, often, there's protections on the data. So we can't just have, huge amounts of ground truth data lying around for retraining every time anybody wants to tweak their scanner. So then you might say, well, let me just train a network for every possible setting that anybody might ever choose on their MRI scanner. That's also pretty problematic. First of all, it's a pretty high dimensional set of possible configurations to sample from. But also when we experiment with it, it doesn't work very well. A third approach that you might be thinking about is more like these plug and play methods. So just try to learn a denoiser offline and then use it for whatever forward model you have or whatever MRI settings you have at the time. But like we've established, that really does not work well when you have a small number of training samples, which again is a common phenomenon in settings like medical imaging. So our proposed solution is, instead of these first three options, is to actually take the network that we learned for the original forward model and make some adaptations to it for the new inverse problem. So we're going to be given a network that was trained for forward problem A0, and our goal is to then take that network and leverage it and make some adjustments to it in order to get a good reconstruction for a new forward model A1. So for example, at training time, we assume that we measure these locations in Fourier space, but then at deployment, something shifted and we measure at these other locations, which are from a pretty similar distribution, but are nevertheless distinct. So the key insight behind our approach is, the key insight behind our approach is that when we learned F theta, when we learned our original reconstruction procedure, we learned something that could invert A0 in a sense, which means that the composition of F theta and A0 acts something like an autoencoder. So maybe this is easier to see pictorially, right? We've got an original image X, we measure A0 times X, we feed that into a reconstruction network, and hopefully what we're getting out, F theta A0 times X, hopefully that's pretty close to X, right? That was our whole goal. So we've learned something that's almost like an autoencoder. And so we're going to use that fact that we have something that's sort of like an autoencoder to design a new regularizer. And the approach that we use stems from this regularization by denoising framework developed a few years ago. Because I'm running a little bit short on time here, I'm just going to kind of skip to the main point at the bottom, which is that we end up with an iterative algorithm that alternates between a data consistency step and a regularization step, like we've seen before. But where the key distinction is the following. In the data consistency step, we're using our new forward model A1. So we're trying to find an image estimate that's consistent with our new forward model, or our new MRI setup. But when we regularize, what we're doing is we're using our old network that was trained for our old forward model in order to perform regularization and ensure that we are capturing structure that's reflected in this old network. So here's an example of this in action, where we just have two slightly different sets of measurements that we're collecting in Fourier space. So in the first example, we have no model shift, right? So this is sort of we knew exactly what to train for when we trained, so this is the best you could hope for. And there we get 31.7 dB accuracy. But if we were to have a slightly different model at test time, just like I said before, we get this 5 dB drop in performance. But by using these model adaptation techniques that I described to you, we're actually able to get back up to the performance that we would have gotten if we had known exactly what forward model to train for from the very, very beginning, without some of these kind of horrifying artifacts. And this is especially remarkable when we think about, different levels of acceleration. So in particular, imagine that we train for 6x acceleration, right? So we only measure 1/6 of the different Fourier coefficients. And then at test time, we think, actually, we've got time to collect more data. Let's only do 2x acceleration. Well, without these model adaptation procedures, if we at test time collect more data than we had at train time, we get a worse reconstruction. So we have worse performance on an easier problem because of this shift from one forward model to the other that I was talking about. But with our approach, this reusing of our old network for regularization, when we adapt to this new forward model, we're able to actually get extremely high accuracy and take advantage of the fact that we've got additional data available to us. And so this is something that we've seen kind of across the board for a number of different networks, where again, the blues correspond to our proposed approach compared to methods taken from transfer learning or that just don't try to adapt to shifts in this forward model at all. And in many cases, we're doing almost as well as the gold bars that correspond to what would happen if we had trained for exactly the right forward model right from the beginning. So to just briefly summarize, I wanted to again highlight some of the key trade-offs that we've explored here together today. The first was thinking about the incorporation of this forward model A into the training process right from the beginning, as opposed to somehow decoupling learning image structure from the inverse problem at hand. And next to each of these trade-offs, I'm just listing one of the papers that you might reference for additional detail for some of these phenomena. Another is trying to look at the number of iterations and convergence guarantees in order to get higher reconstruction qualities. And then finally, trying to ensure that these methods are robust even in the presence of model mismatch. So with that, thank you very much again for the invitation to speak with you all today. I will leave this slide up here and I'd be happy to answer any questions.
Yeah, thank you, Rebecca, for this great talk. So the talk is open for discussion and we have time for 1 or 2 brief questions. So you can either raise your hand or talk or post in the chat. So it seems Peter posted something, but it's not quite complete. So there's a raised hand here.
It's only me if nobody else raised the hand. I was just wondering when you said this fixed point, I mean, it depended on the data, but that wasn't explicitly mentioned. So I was wondering, how did you get rid of the data dependence? Is it via the averaging in the loss function, or otherwise it would depend each time you have a different data, you get a different theta, right? I would think in the optimization procedure.
Right. So I think I wasn't perfectly clear. So the data here is y, and so you're right. This function is sort of dependent on y, and so what we're trying to do here is learn a theta so that whenever I plug in whatever y, then the resulting fixed point is a good fit to the corresponding image x. So I've got these like xi, yi pairs. So for each yi that I might plug in here, I want the corresponding fixed point to be close to xi. So I'm trying to choose the theta that's going to work across all the different xi, yi pairs. So you're right, it was not very explicit in the notation here, but it is not, but this is something that varies with y.
Right, okay, yeah, thank you for the clarification.
So I see in the chat that Peter said, what happens if you've got a model like y is equal to a plus e in parentheses times x? And I assume that, but correct me if I'm wrong, I assume Peter's thinking that a is known, but e is not known.
Yeah, error. So if you have error in the model, what would happen then? So I think that what you discussed the last probably is kind of in this direction. And
Yeah.
I hope that you have some thoughts about this.
I've got some empirical thoughts. So in this last part, I talked about the setting where at first we've got data from A0, and then later we've got data from A1, and we want to adapt to that. And so the methods that I described and focused on here assume that A1 is known. We've also done some empirical explorations where A1 is not known, but it's assumed to be close to A0. So it's a relatively small perturbation from A0 in some sense. Like either there's a low dimensional parameterized form that we can search over, or it's close in some other sense. And there, what we can do is we can somehow jointly optimize over the new reconstruction and our estimate of A1. So if we think of A1 as being A0 plus error, and we don't know the error, then we can do that. So that's seemed promising in some of the examples that I've described here today. So for instance, MRI, where we've got some shifts in the K-space locations. But I think that my feeling is that in general, the efficacy of these approaches depend on how big that error E is, or how different A1 might be from A0. And the bigger that gap is, the harder it's going to be. And so that's something that I don't think we really have a thorough understanding of on a mathematical level. Like, how do we even measure the closeness, or under what settings can we somehow adapt to those errors? How big are those errors allowed to be? I don't think we've got good answers to any of those questions at this point.
So the next question would be by Ben Adcock.
Thank you. So thank you, Rebecca, for a great talk. That was really interesting. And thank you also for mentioning our paper. It's really cool that you've taken one of the effects there and tried to solve it and done pretty successfully. So I was just wondering, so in that paper, as I'm sure you're aware, like we also show these other types of instabilities of trained neural networks. So in terms of like small perturbations of the measurements, and also small features that are not in your training set that get washed out by the network. And this is kind of not just us. This is now, like, if you look at these results from these fast MRI challenges and stuff like that, you see discussion about AI generated hallucinations and things like that. So do you have any kind of general thoughts on these, and how susceptible your networks are to these, and how you might go about resolving these issues?
Yeah, yeah, I think these are great issues. They are, a little bit, related but distinct from some of the things I talked about here. With respect to some of these AI-generated hallucinations, I mean, let me kind of recast it slightly. So imagine that we want to reconstruct images of brains, and we want to do this in a way so that we're going to be able to detect tumors, but we don't have like a whole lot of tumor-ridden brains to train from. And tumors can be lots of different shapes and locations, et cetera. And so we want to be able to make sure that just because we don't have a lot of tumors in our training set, we'll still be able to reconstruct those tumors. So my general thought there is that we can gain a lot by methods that try to learn, instead of models for full images, instead learn models for image patches. So if I think about, the full huge MRI image is just being a tiling of different image patches, and think about the geometry of those patches, I imagine that that's somewhat lower dimensional and simpler, and allows us to kind of learn geometries of tumors in a way that's agnostic to where exactly it's located in the brain. And so we've done some experiments with, implementing these kinds of approaches over patches as opposed to over full images. And it does seem to make an improvement, but that was all in a remote sensing context. And so, I think these are some limited empirical studies that show some potential but aren't fully understood. I think they are still open, challenging questions. And in terms of robustness to small perturbations, this is also something that we explored. We really enjoyed your paper and thought it asked a lot of exciting questions. In our experiments, we found that, small random perturbations on average were not having a big effect, that you could find sort of adversarial perturbations that could have a big effect, but those were really the exception rather than the norm. And so that seemed, in our minds, to be somewhat less of a huge priority than some of these things about like robustness to tumor shape and location that I just mentioned. but nevertheless important, right? Like, I think these things are exciting. I think there's a lot of potential. And I also think there's a long way between the mathematical questions we're trying to answer here and something that could be used in any kind of clinical setting.
Yeah, I'm glad you said that. I think that's my impression as well. So anyway, thank you again.
Yeah, thank you.
So there's one more question in the chat by John Harlim. So the convergence is defined on empirical loss. Can you mention about the generalization error?
Yeah, so in all of the different plots that I showed, for instance, all of these are results on a test set that was not used at all during training. And so our hope is that is a reasonable estimate of generalization error. But of course, as with all of these different machine learning tasks, you're kind of limited to what extent your data set has been carefully curated, right? So if you want generalization with respect to the distribution that all your training images and test images were drawn from, then I think we're doing fine in that sort of generalization. But I think if you wanted to say something about generalization to a slightly different distribution that, say, contains more, tumors, then there's not much that we know how to say at this point.
No, actually, the follow-up is actually the questions from Sebastian, right? So basically, the convergence that you are studying here is basically just telling you the consistency with respect to the training image, so that you are doing analysis on the empirical loss functions, right? But if you want to study the mathematical analysis of the generalization error, is there such a, I think, is it still open, or in terms of doing this?
Yeah, I think it's still very open. I mean,
right.
Often when you
numerically, I agree. I mean, I saw what you showed numerically, which I'm fine with that. But my question more or less is the theory.
Right. So we can, you can prove that, as long as and this is not ours, this is just something that's generally known, right? If you've got a function that's contractive, then, then it's got a fixed point and you can find it, right, using fixed point iterations. But I think, an important question is, what's the nature of that fixed point? Like what function space are these fixed points going to lie in? And if I were to change my neural network architecture, then how does that change that function space? So in particular, we've been working on these things for quite a while. When we first started, the architectures that we were using were UNets and MODL. And more recently, we've been doing some experiments with a denoising CNN architecture, and that's given us some big performance benefits. But I don't think anybody has an understanding beyond sort of a hand-wavy intuitive understanding of why that's the case. Like, do they correspond to different function spaces, or is it that we can they result in sort of a loss landscape over the space of network parameters that's easier to traverse and easier to navigate using stochastic gradient descent? And so, yeah, I think those are some big questions that are wide open and very poorly understood, not just in this context, but in deep learning in general.
Thank you.
So thanks again to Rebecca. And so it's time to move on to our next speaker, Sebastian Reich. You can share his slides now.
Okay, can you see them now? Yes, right?
Mm-hmm.
Okay. Yeah, so thank you also for inviting me. And
just a moment to introduce you.
Okay, sure.
So Sebastian Reich is a professor of numerical analysis at the University of Potsdam. And his research focuses on numerical methods for differential equations with applications in molecular dynamics and data assimilation. He holds a honorary visiting professorship at Imperial College London and was also named a SIAM Fellow in 2019. And the title of his talk today is Statistical Inverse Problems and Affine Invariant Gradient Flow Structures in the Space of Probability Measures. Please go ahead, the floor is yours.
Right, Marcus. So thank you for the introduction and for the invitation then. Right, so I will talk a bit more on sort of abstract level of computational methods, but there's a strong link to what Rebecca just talked about, because basically one example I want to look at, or I use as an example, is regression. And in Rebecca's talk, the G was the A, the theta was the X, and the T is the data in my context, and it was the Y in Rebecca's case. And I think you, Rebecca, you focus very much on the construction, what I would call the prior or the regularization term. So in my talk, I will take this as a given, and then basically ask myself, how can we do Bayesian inference, computational Bayesian inference in this context? So this is one motivating example for what I'm going to talk about. And the second one is logistic regression. And I wrote down here the likelihood function for binary regression. So where the data is either 0 or 1, and this is a logistic function, and the theta here, theta x, is a feature map. So these two examples will sort of guide us throughout my talk. And the reason why I chose them is because they in a way very nice and can be fully understood, but then they generalize very easily, as we saw in Rebecca's talk, to really highly complex tasks. So in particular, if you look at the regression case here, then this function, the negative log likelihood function, is very nice, bilinear function. And if you also assume that the prior is Gaussian, then you have some sort of Tikhonov regularization. And there are, if you put this into a Bayesian context and you want to look at the posterior distribution given a prior in this way, where the theta is the mean and the sigma is the covariance matrix, the prior covariance matrix, then Kalman's formula tell you basically how to update these two quantities from the prior to the posterior given the data. And the Kalman formulas are nice because they involve this Kalman gain matrix, which sort of tells you how to, for example, update the mean and how it is informed by the data. Anyway, these formulas goes back to the 60s, and I mean, this formula is just to rewrite what we saw at the very beginning of Rebecca's talk. The only quotation mark difference here is that we also update the uncertainty in a way, so the variance. But if you're only interested in minimization, then of course you just look at this this formula, and that formula is valid for this very simple Gaussian prior. Now, logistic regression gets a little bit more complicated, but it's still sort of a nice example, because even if you start with a Gaussian prior of this form, because of this logistic regression and sigmoidal function, the posterior is no longer Gaussian, but it's the minimization problem is still very nice. So the map estimator is well defined, and it's a convex function in minimizing, but the whole distribution is no longer Gaussian. So it's a little bit more complex than the linear regression with a Gaussian prior. Of course, in practice, you often have nonlinear function here, or as we learned in Rebecca's talk, you might use more complex priors. But the methods I will talk about today, they're basically applicable to those situations as well, at least in principle. Okay, so now the computational methods I want to talk about are Monte Carlo methods. for the reason that they generalize more easily to more complex tasks, and they will suit it for Bayesian inference. And so basically, the challenge is in all these Monte Carlo approaches to produce samples from the posterior, whatever the posterior is. And if it's one of the two examples I just told you. Now, the thing is that basically, there are many ways how to do this, and in particular, how to relate this to your prior. And in particular, this connection to the prior distribution is actually not specified by Bayes' theorem. Bayes' theorem tells you this is a distribution, right? And but it doesn't specify a link in terms of random variables between the prior and the posterior. And if you look at the available computational methods, then they, broadly speaking, fall into two categories. So one is based on coupling, explicit couplings between the prior and the posterior distributions. So you basically can think of Bayes' theorem giving you the marginals, right? You have a marginal as the prior, and the other marginal is the posterior. And the coupling means that you find a joint distribution which links the two objects together. And again, the Bayes' theorem doesn't tell you anything about it, it just tells you about the marginals. And the other broad category of methods, which are probably much more widely used so far, are those on invariance ergodicity. So you construct processes, stochastic processes with certain properties. Okay, let's first recap the coupling idea. I basically already gave it away. So we have a prior. This is the prior distribution, as I said, can be Gaussian. Then this is the posterior in logistic regression that's no longer Gaussian, but it's well specified by Bayes' theorem. And then basically the concept of coupling is to find a joint distribution with these two marginals. And of course, you can write this joint distribution then disintegrated into this form, the prior and the transition probabilities. And once you have this orange object, then you can convert samples from your prior easily into samples from your posterior. So this is the whole appeal of this method, right? So you have this, once you have such a coupling, then, and you have samples from the prior, which we often have, for example, in sequential sort of estimation problems, where like the prior relies on data you already assimilated or used previously, and you want to update sort of through the incoming new data, then such an object is often represented by samples itself. And then having such a transition probabilities makes the transition to the analysis or the posterior very easy. So maybe I didn't say that. I'm using a little bit of geoscience jargon. So the forecast is equal to prior and analysis is equal to posterior. So forecast, analysis, prior, posterior is exactly the same thing. It's just notational that I use it with F and A. F like prior, A like posterior. Now, clearly, such a joint distribution is not uniquely determined by the marginals. And so you can, for example, think of optimal transportation under some cost. Or if you think more stochastically, you can embed this into Schrödinger pictures, et cetera, et cetera. And then there's a link to stochastic optimal control, et cetera. But of course, you're not restricted to this. These couplings are then specified or by some sort of cost functional. So here's one coupling, which is closely tied to the linear regression example I started with. So remember, I told you that for linear regression with a Gaussian prior, you have the Kalman formulas, which give you an update in the mean and the covariance matrix. So this itself is not yet a coupling. It just tells you how to propagate the first two moments. And of course, if everything is Gaussian, then the problem is solved. But you can also think of how can I do this in this coupling framework. So it's basically trying to find for this specific problem a transition from the forecast or the prior to the posterior. And one of the forms is this one, which is very nice and easy. And was sort of discovered in around 2000, a little bit before 2000. so quite a bit after Kalman's original work. It's become extremely powerful and used in many fields. So the coupling is basically defined. So you take your Gaussian prior random variable and you correct it through this term, which looks like is the Kalman gain. And here is sort of the data misfit term, like your forward model minus the data. And then to lead it to to achieve the correct coupling so that the first two moments of this object agree with Kalman's formulas from the 60s, you have to add this noise. So this is the interesting term. If this would be out, then this looks like the update for the mean in linear regression. But this term then also guarantees that the variance of this object is correct as well. It's an easy sort of calculation to show that if this random variable is Gaussian with these two moments, then the implied random variable theta A has the correct first two moments. And because the whole thing is linear, it remains Gaussian, so everything is fine. And it's easy to see, in particular, if you take the average, then this term, of course, drops out because it's just a Gaussian random variable, independent of anything else. So you end up with the update for the mean. Now, this is a coupling that's neither optimal in an optimal transportation sense or in the sense of it's not a Schrödinger coupling, but it's still a very appealing coupling. And we'll see later in this talk why actually it is such an appealing coupling. Okay, so this is a coupling idea, and we will come back to this later in my talk. The other approach that probably most of you or many of you are maybe more familiar with, of course, Monte Carlo type of methods, where I would say instead of coupling, you successively decouple, because basically what you do is you define a sequence of random variables so that in the limit, the process samples from the desired target distribution, and the whole thing has to basically satisfy two constraints. If you initialize it in this distribution, you should stay in this distribution. That's invariance. And then if you're outside this distribution, you hope you go there. So this is the ergodicity argument. And but that also means that basically if you start the process in the prior distribution, that as time goes tau, time goes to infinity, things become independent. So you actually lose any coupling. And so this is rather achieving independence in the long run, which is what you desire in this context. The price you pay, of course, is that you typically have to run for a long time to achieve this. And of course, the standard example is Brownian or Langevin dynamics, where you have a drift term, which is the negative log likelihood function or the gradient of the negative log likelihood function, or the posterior in this case, if you want to do Bayesian inference and you add noise to it. I would assume that most of you have seen this and are aware that this has the right invariant measure. And in a discrete setting, you have the Markov chain Monte Carlo methods. Okay, so this was sort of a warm up, and maybe that's actually a good moment to take maybe a short break in case there are any questions in terms of clarifying what I just said. Maybe something notation wasn't clear or something I said wasn't clear. If that's not the case, then I sort of would continue with what I now gonna cover in the rest of the talk. So basically, it's a concept of affine invariance, and as I said, that's an appealing property that this Kalman coupling has, which I talked about earlier. And we will generalize this. We also see that basically this Kalman formula, I mean the coupling of Kalman, the coupling formula of formulation of the Kalman filter or Kalman update formulas leads to interacting particles. And then we will explore this. And then we will look at mean field limits and continuous time limits. So to see what the mathematical structure is that arises from these sort of aspects. And in particular, we will see that there's a gradient flow structure emerging, which is a generalization of the work that Felix Otto started and many others have explored since, sort of this gradient flow structure of the Fokker-Planck equation, for example, and other equations. And finally, we'll say a few words on numerical implementation. So that's the program for the rest of the talk. Right, so what's affine invariance? I mean, numerical analysis people normally are quite familiar with this. In the MCMC literature, it's also become more and more popular because these methods seem to outperform other methods in general. So let me remind you of what it is. So the method of gradient descent was already mentioned in Rebecca's talk. So in a time continuous framework, not in an iterative way, but going to the limit of taking infinitely small time steps, you can think of this as an ODE in descending in the direction of cost functional. And it's a method for finding a minimizer of this cost function V. The thing is that this method, even though it's widely used, for example, in machine learning in various incarnations, but it's not invariant under linear transformation. So if you reformulate your algorithm in the variable theta hat instead of theta, which is related to theta by this affine transformation A being invertible, then you find that if you take this algorithm and you then reformulate everything in theta hat, you get a different algorithm, so to speak, right? Because suddenly you have this preconditioning matrix here, which involves the transformation A. And the method is called affine invariant if that's not happening, right? So if by some magic cancellations, the algorithm looks the same under all affine transformations. And of course, we know the numerical analysis people among us certainly know that Newton's method, for example, is affine invariant. So that's one of the reasons, of course, why it's so popular. But it's also the case, without going to the explicit calculation for now at least, it's also the case for this Kalman update formula, which is widely used in the geosciences for doing Bayesian inference. So this has also this nice property, and we'll see why in a few minutes. Right, so now, we have the concept of affine invariance. So how do we get it? We will get it through many particles running basically coupled together. And then this affine invariance will pop out for free in a way. And of course, the most naive way to get particles, several particles, is not to have them interact. And so this is an example. So you just have the Langevin dynamics. I mentioned this already as a way of sampling from a certain distribution. And of course, you can run many copies of this parallel to, let's say, get a better statistics of the distribution at a certain time. Indeed, so if you have to take the empirical measure that comes with m copies of this, which run independently because the noise and the initial conditions, let's say, were chosen independently, it will converge weakly to in the limit t to infinity to the desired distribution. So you can then compute. And furthermore, if you look at this is actually, again, your gradient descent method, now just run in multiple copies. So it's also not affine invariant. So the method is not affine invariant as the stochastic or as gradient descent and its stochastic versions. Okay, so how to get there? First of all, we know that basically the time tau marginal distribution satisfies the Fokker-Planck equation. So if you have Langevin dynamics and you want to know how the solutions are distributed at time tau, then the direct evolution equation for the distribution is the Fokker-Planck equation, which is this equation, or written more explicitly in this form, if you have the specific form of the potential. The Fokker-Planck equation is also not affine invariant, but it got, of course, a lot of other nice properties. It is of this gradient flow structure. So you can write the Fokker-Planck equation in this abstract way. So it involves, it's basically a gradient flow where the potential is now not just the cost function itself, but it's the Kullback-Leibler divergence between the current distribution and your target distribution, which in our case is the posterior distribution. So the Fokker-Planck equation minimizes Kullback-Leibler, and it's a gradient flow. The gradient is defined by this equation. And I said that was the discovery of Felix Otto and other his collaborators, to see that this is basically what's happening. So here, this is the variational derivative of Kullback-Leibler with respect to the first argument in Kullback-Leibler, and that's then the gradient of the functional of the function you get from this. And it turns out it's exactly the equation I had on the previous slide. And furthermore, as for gradient flows, it minimizes. I mean, it's non-increasing, of course. And of course, there's lots of interest in how quickly that happens. That's not an issue in this talk here. But the important thing is that we have this gradient flow structure now in the space of probability measures. So that's something we want to keep. So we now want to get together basically Monte Carlo somehow, this gradient structure and affine invariance, and all hook it together also not also with the Kalman filtering. So that's where we're gonna get the idea from. And so here, I mean, so far I basically told you about non-interesting sort of couplings. So this non-interesting interacting particles, right? So they didn't actually interact at all. So now if you look at this, get back to the Kalman formulas, then that was sort of the update from a prior to the posterior. And basically, we can use this coupling, which I wrote down earlier, which involved this Kalman gain and was sort of a linear transformation formula, otherwise from the prior random variable to the posterior random variable, to just plug in empirical estimators if you have m samples. And so the only thing that really changes now, if you do this in the Monte Carlo implementation, is this gain is now being computed using empirical estimators for the mean from the particles or from the realizations you have, and the covariance matrix, empirical covariance matrix from the samples you have. So this is the only thing you really have to change when you go from this mean field coupling equation I wrote down earlier, which is exact in the linear regression case where you have a Gaussian prior, to when you only have samples, which is often the case where the prior is represented only by samples. And furthermore, this formula can also be applied regardless if these samples really come from a Gaussian distribution. Of course, then you make some errors and one has to study these errors, and that's an active area of research. But you can certainly apply this regardless of the assumption that this is necessarily coming from, these are realizations from the Gaussian random variable. And that's it. Remember, T is the data, G is the forward, so G would be the A operator, and K is sort of the gain that is defined down there. And again, the coupling of these particles comes through the gain, right? So that's the only way the coupling appears. Okay, so maybe again a good moment to just take a short pause, because what I'm gonna do now is to put all the things together. So we basically have the Langevin dynamics picture, we have Fokker-Planck, we have a gradient flow structure in the space of probability measures, we have Kalman formulas. Now we have an interesting interacting particle system, which is used widely in practice, which is used on the idea of coupling Gaussian measures based on Kalman. And now we're going to proceed. But anyway, it's just a short break in case there is any question. Okay, no, there isn't. Then let me proceed. So to see a bit more of the common mathematical structure, let me go to a time continuous version of this. right? So to make the connection to Langevin dynamics and the Fokker-Planck equation, let me reformulate this in a homotopy way by going from time 0 to time 1 in this way. So this formulation, again, there are many couplings and there are also many implementations of these Kalman formulas. So this is one particular homotopy, but it's a very nice homotopy, as we will see. But it's doing exact inference, so to speak, if you look at linear regression and the Gaussian prior, and the posterior is also Gaussian. And the idea is that you write down a differential equation, a mean field differential equation, which is again involving some sort of statistics of your random variable, but otherwise it's sort of an ordinary differential equation. And you evolve this over 1 unit of time. You start with your initial conditions distributed according to the prior, and then you solve these equations, tau being time, so t again, t is not time, t is the data, so it's fixed, tau is time here. And you just integrate from 0 to 1. And then it basically does the same as this. This is a slightly different coupling than this, but in terms of the statistics, the mean and the variance is doing the same thing. Okay, but this has blue and red terms. So it turns out that the blue terms are the gradient of a potential, of a cost function. And the sigma is, again, the covariance matrix associated with the random variable theta at any time tau in between 0 and 1. So what this is sort of gradient descent, but now in a sort of a mean field context, but it's preconditioned. This is key. So the Kalman formulas lead to this preconditioning by the covariance matrix sigma, which is easy to compute if you have Monte Carlo samples from the distribution. And so this is maybe a bit dense here, but basically the blue term is the gradient of this blue term down here. So it's a little bit complicated, but you have a function of theta, which is tau dependent. Again, it involves some mean and sort of, it's not just the variable itself, but depends on the statistics of this variable. But just take it. And then, as I said, the important thing is that there's a sigma. So you can basically, with this ODE, you can write down not the Fokker-Planck equation, but the Liouville equation. So there's no noise. That's why it's a Liouville equation. So this is the evolution equation for the marginal distribution of the theta, right? It's for the distribution of theta. So that's just the Liouville equation. So that describes this. And here is just a shorthand what's been written here. If you do, crank the handle and you calculate for the things I have here, and we know that this is Gaussian if look at linear regression and the prior being Gaussian, then this is Gaussian. You can calculate all these the divergence here and can go through it. It turns out it's exactly this thing, and this is the likelihood of the data under linear regression and minus its mean, and that's a distribution. Now this here is the homotopy variant of Bayesian inference. So this is basically, if you want to write down Bayesian inference not as prior times likelihood function, but prior being sort of evolving in time 0 to tau equal to 1. So this is a differential equation form of Bayes' theorem. And that's, of course, if you integrate this equation over time tau, then, and you initialize with the prior, then we know that this at time tau 1, that's the way we set it up, gives you the posterior. So this is exactly the right equation. One, I mean, it's not unique, right? So there are several equations that achieve the same thing. But this is the idea behind, in a nutshell, behind this mean field representation of the Kalman equations in a time embedded way. And this object here guarantees you the affine invariance. It's very easy to implement, right? Once you think as a Monte Carlo method, and this Liouville equation is now affine invariant. And that also leads, of course, to the interaction between the particles. Now you can reverse this sort of thing and generalize it. Because you can basically, what you can say now, I can solve any Bayesian inference problem by generalizing what I just did for the Kalman filter, by saying, I take this general framework. So I precondition gradient descent by the covariance matrix. And I have a more complex potential. So it's not just the loss function, some data loss function, but it's more complicated. And I set it up in the following way. Now I start from the homotopy approach to Bayesian inference. And I say, I want to reformulate this part in terms of a Liouville equation. So in the previous slide, I started with this, which Kalman magically gave me, and I found that this is true. And now we go the other way around. For any, like say, logistic regression, you take this, and this can be now any distribution, then you solve, given this right-hand side, as a given at any time. Now you solve this elliptic equation for this potential, and then you stuck it in here, and that gives you the evolution equation for the distribution, for the random variable theta. And with this, you can, in principle, if you're able to solve this elliptic problem, you can solve any Bayesian inference problem now in a time continuous way, which of course you eventually will discretize in time again. And at time tau equal to 1, you get to the and so implicitly, then it also defines the coupling through this evolution. And as I said, now this approach can be, when it goes beyond the Kalman filter, which works for linear regression and Gaussian priors. The important thing is that this now is affine invariant. This gradient flow is affine invariant. And the further catch in all this is that it's not only that it is of this type in the case of the Kalman formulas, but it's actually, it also leads to a generalization of what Felix Otto did with respect to Fokker-Planck. So the Kalman equations in this homotopy approach also have a geometric structure exactly as the Fokker-Planck equation. The only differences are twofold. First of all, you have a different potential. So it's no longer Kullback-Leibler, but it's this function which is related to the data likelihood, right? So the cost functions are different from Fokker-Planck. And also the gradient structure is a little bit modified because you have, again, this covariance matrix appearing here. So it's a sort of an different inner product. So instead of having just the Euclidean distance, you have the Euclidean distance weighted by the covariance matrix of your random variable. And so you get a sort of a modified gradient flow structure. But otherwise, it's exactly the same thing. But this modification has a nice impact that this gradient flow structure now is, again, affine invariant. So if you change to a different linearly related coordinate system, the equations will not change, which again is very attractive from a numerical point of view. And this suggests the final step of today, so to speak, in my talk, because now once you have realized that this structure is there, then you can of course say, okay, now I can also go back to Fokker-Planck, and I just replaced this, which is was now motivated by looking at the Kalman filter and its mean field formulations. Go back to Kullback-Leibler, and so that's again sort of just an almost trivial modification. Now all you need to do is to stuck in the covariance matrix in there, and of course replacing this gradient flow structure, the original gradient flow structure, which is in the Fokker-Planck equation, by something that you put in some operator in front of the variational derivative has now become very popular. For example, if you think of Stein variational gradient descent, then that operator is not the covariance matrix, but it's the kernel operator in a way. So it's a convolution that appears here. But and that has other benefits, but this is another approach where inspired by some, in this context, machine learning and Stein's method, people have devised modifications of the Fokker-Planck equation, and it can be thought of as introducing some modified operator in front of the derivative of Kullback-Leibler. And the same, you have still, of course, a decay property. Right, and so if you do this, then you end up with a modified, actually now nonlinear Fokker-Planck equation, and it's affine invariant. And its implementation is very straightforward, right? So in the mean field context, at least, if you want to relate this Fokker-Planck equation actually to an SDE, then you get this, which looks at basically, if you ignore this term, it looks like the things we had before. When I talked about Bayesian inference and the homotopy approach, then we just said this potential is defined by an elliptic PDE, which comes again from interpreting Bayes in a proper way. Here, the potential now is actually again given by the posterior, as in Langevin dynamics, and instead, so to speak, you now add noise, and you have the square root of the sigma appearing here. That's sort of the price you pay, but it's structurally of the same type. And furthermore, before in the homotopy approach, we integrated here from 0 to 1. Now here, this is rather the decoupling approach, where you have to integrate the tau to infinity, and then you sample from the right distribution. Now there are lots of interesting mathematical questions. For example, you should make sure that this is not getting singular, and we were able to show this. And we also, I mean, the easiest thing is to show that the invariance, that's quite easy. But then to show that you also, under the usual assumptions, have agodicity, and so things like this. This has been discussed. Now, another issue, and that's sort of winding down in a way already, is this is again sort of a mean field equation, and you want to implement it. So then you go to realizations, and you basically do this by running multiple copies of this model here. But now these start interacting again just through the covariance matrix, and you have to be a little bit careful, because once you replace this by an empirical estimator here, then this you have to think about Stratonovich and Ito and things like this. So it's becoming multiplicative noise. So the invariance is not so easy to guarantee. So in fact, to get invariance to the right measure, even for finite number of interacting particles, you need such a correction term. But that's sort of easy. It's just a linear term that actually repels a little bit, because this becomes a little bit too constructive. But you also see that it's divided. D is the dimension of state space of the estimate of the parameters to estimate. M is the number of particles. So if M goes to infinity, this term goes away. So in the mean field limit, this term goes away as expected. And as I said, the orange term is needed for invariance, and invariance and agodicity of this whole system can be shown if you have at least as many particles as the dimension plus 1, and affine invariance holds regardless. And there are other nice features about this, which also has made this Kalman formulas very attractive in for nonlinear regression, etc., because you can avoid, at least conceptually, you can avoid taking derivatives, which, sometimes you might say, okay, in machine learning, backpropagation, all fine, but geoscientists and other applications, the derivatives are not always so easily available, and so then avoiding derivatives is maybe a good feature. So let me as the last thing, just say a little bit about how to achieve this. Basically, one way to achieve this or to justify such an approximation is to not take the variance essentially of your whole ensemble globally, which might not be a good preconditioner anyway, because if you have multimodal distributions, the whole Gaussian of the whole distribution is not good. You might want to have a more local estimate of the second moments, and you can do this with such a tempering function, sort of where you sort of temper your distribution with a local Gaussian, and then you basically get a localized version of the covariance matrix. And the fact is that if you now look at this is the original distribution, this is this tempering. Then if you look at this as a combined distribution, localized, then this will look very much, this will start dominating, and this is Gaussian on its own. And then you can actually make such approximation. So basically the covariance matrix times the gradient becomes approximately the same as the covariance matrix times the average of the gradient. And that under Gaussian approximation is strictly the same as the covariance matrix. And so this allows you to basically replace covariance matrix times gradient by correlations. And that's often used in practice, even though maybe sometimes also outside a strict range of validity. But it's certainly quite a powerful benefit of this approach that this can at least be easily implemented, and it avoids computing gradients. And here's an example where basically you have a bimodal distribution, and if you do this derivative-free approach now and you don't localize, then you screw it completely up. I mean, derivatives are clearly not the right things. I mean, or the representation of the derivatives by this, replacing it by correlation is not the right thing. But if you localize it, it all works well. So, and that can be justified, as I said. Okay, just to finish, basically what I talked about is, on the one hand, I talked about this transport or homotopy-based approach to Bayes, which sort of started being popularized in around 2010. Freddie Daum, Josef Masurk, and myself, and in a slightly different context, also Dan Krishan at Imperial. So all around the same time, basically. And then, as I said, another big ingredient for today's talk was the gradient flow structure, which was pioneered by or discovered, popularized by Felix Otto, and recently has gained again in popularity through this variational Stein variational gradient descent methods. Then, as I said, yet another ingredient was the affine invariance, which is widely used in numerical analysis, but in Markov chain Monte Carlo literature, Goodman and Ware, Jonathan Ware, 2010 sort of popularized the idea. And as I said, if you look at a lot of the currently popular methods, then they satisfy such properties, and in particular instances are by a thesis on Greengard, and then work by Ben Limekuhler, and again, Jonathan Ware and Matthews. The ensemble Kalman filter, as I said, in this mean field and sort of coupling perspective, even though it wasn't, Gary Evanson is a geoscientist, so he was, I think, more coming from a very practical end, was invented in around 1994, and there's also a book by Gary Evanson. This sort of time continuous approach to the Kalman filter and related algorithms sort of came in my group, and then we picked up by Stuart, Claudia Schillings, and many other papers. Now it's sort of become popular also as a mean to solve minimization problems. Now the associated, when you look at these Kalman-Busse equations, as I call them, the time continuous formulations, and the gradient flow structure that comes with it, which Andrew Stewart and his group is now calling the Kalman-Wasserstein gradient flow structure, was sort of considered in these papers. And the sort of last algorithms I talked about, this modified Langevin dynamics, again, was sort of worked on in the group of Andrew Stewart and in our group. And there's now been a lot of interest in extending these ideas, logistic regression and neural networks. So that's a little bit of the literature on this in the history. And then sort of What I didn't cover in my talk, but which are all very interesting directions, is sort of, I just look at the single inference step, but I already mentioned sort of the real power of these methods come into play when you actually do this sequentially, where your prior is actually defined as part of the process. And that gets maybe back to Rebecca's talk as well, where the prior was not a thing that was a priori set, but was informed by the data and updated through the data and was learned on its own. So this, I think, leads into the wild world of sequential learning and filtering. Then, of course, there's a lot of interest now to think of this as an optimal control problem, also in machine learning, recurrent neural networks or deep neural networks. So thinking of actually sort of control problems we're solving there. And of course, these problems from a mathematical perspective are linked to Schrödinger bridges. And then from a more practical point of view, there's of course sort of techniques as stochastic gradient dropouts, localization, random feature maps. So these are all algorithmic hacks which can be built into this framework and which we try to understand what they're doing and what their benefits are. For example, we know now that stochastic gradient descent can be understood as a stochastic perturbation. I mean, if you, in the sense of modified equations, which is a nice way of thinking about it. And of course, there's basically an exploding literature on sort of interacting particle systems for all sort of purposes, algorithmic purposes, whether it's optimization or whether it's sampling. There are so many choices to make and avenues to explore. What I talked today about was sort of just the first steps, I think, a few of the first steps in this direction. And with this, I end, and thank you for your attention, even though it's getting late, at least in Europe. Thank you.
Well, thank you very much for this very interesting talk. So the talk is now open for discussion. Are there questions? So we have a first
John, I guess. I see John has raised his hand.
Yes. So you should be able to ask now.
Yeah, sure. Hi, Sebastian.
Hi, John.
Thanks for a very nice talk. So if I understood this well, the general context is that you were basically, there's one approach that in order to sample posterior distribution, you're constructing a Langevin type dynamics, and then you embedded, you also embedded sort of Kalman filter algorithm in and then justify it using the mean field formulations, right? So now the question is that, like, compared to the usual MCMC, usually you do have to visit the likelihood function so many times in order before you achieve a certain sets of parameters that reflect the posterior distribution. And then the other issue with the MCMC that I think is quite common is that the dimensionality of the parameters, right? So how does this new, I mean, maybe this is not a new idea, but I just heard about this. It's like this idea of like constructing these dynamics as an alternative of sampling. Now, if you need to march an ensemble up to a certain time, and in one of the slides you're saying you forgo the homotopy from 0 to 1, then you sample up to time infinity. So that means you have to discretize this SDEs in a very careful manner. And then that basically also means every time you solve this SDE, this ensemble of SDEs, you need to revisit the likelihood function anyway with so many times, right? So what are your thoughts about this, right? And then how does this method will actually hopefully overcome the curse of dimension, or is that even possible or not?
Well, I think that you raised, I mean, the whole lot of questions here, right? So the first thing is, as I understand correctly, sort of equilibration. I mean, your priors, let's say, really off, and then it might take a long time before you recover, you get close to the posterior, right? So this is equilibration issue. And then there's another issue with dimensionality. I mean, how does it all scale up with dimensionality? Now, in terms of equilibration, I mean, in principle, I mean, like this homotopy reduces everything to integrating between 0 and 1. So this sounds like brilliant, right? So you're done in finite time, right?
Yes.
But of course, yes. I mean, the equations are generally speaking, very stiff. So you need very good time integration methods. And that's not directly resolved by affine invariance. I mean, it helps you, right? I mean, we know, like, you do gradient descent and you might have to take very small time steps just because you have one direction which is very fast and one direction which is very, very slowly evolving, and then your method becomes very inefficient. That is resolved by affine invariance, right? And that's the same true for these methods. So if that's the case, that you artificially introduce some poor scaling in your variables that lead to stiffness, that's resolved by affine invariance. Now, however, if your prior is far away per se from the posterior, that's not resolved by this method.
Okay.
Not directly, of course. You know, by using this homotopy between 0 and 1, you, as I said, if you have maybe a good numerical method, you might still avoid this issue of stiffness, and we have numerical methods like linearly implicit methods that can do it. And again, there, the Kalman update formulas help you actually, because they actually the perfect time stepping method for the homotopy method itself. So basically, let me say this: so you have a discrete propagator basically by the Kalman formulas, then you go to the Kalman continuous limit for theoretical purposes, but then don't use Euler or any of these sort of standard methods to go back, but really use the method where you got from, namely the Kalman formulas. And they like the perfect update. They're very robust and they like linearly implicit time stepping method. So as long as you stay sort of close to a Gaussian or nearly Gaussian regime, it is still a very good time stepping method using the Kalman formulas itself. Instead, let's say an Euler method or any of those. But these are really two different issues, right? So affine invariance, scaling of variables, and then the distance between the prior and the posterior. They need different techniques to be resolved. And then, yeah, cursive dimensionality. Well, what can I say? Not much in my talk here yet. I mean, that's not per se addressing it, except that you can think of particle representations as a model reduction, where you sort of collapse the very high dimensional problem into a subspace where you actually solve the problem. And that's defined by your initial ensemble. So if your initial ensemble is chosen wisely, then that amounts to a model reduction, and then it can be very efficient. So it might be able to address some of the issues with high dimensionality. But that's almost another talk. I'm currently thinking about this also with regard to standard machine learning techniques, kernel methods, in as far, and that's related to these random features. I mentioned at the very end, because the random feature maps, you can think of how to initialize these algorithms in the Monte Carlo context. And again, random feature maps, if they're chosen good and well, then they can be very efficient. But again, this would be another talk. And I didn't touch on it in my talk here.
All right, thank you.
All right, so if there are no further questions, then again, many thanks to both of our speakers for the great talks today. And this closes today's session. So we continue again with the last FoCM online seminar in 1 month. And now there will be the opportunity, we will leave this room open and give everyone the opportunity to unmute themselves and turn on the camera to have a bit of a chat.